Hello everyone. This is a data structure class. We have finished the midterm exam now, so we will start the second half of our class. So second half, uh, our class start from chapter 4. Chapter 4 is about linked list. Okay, so so this linked list. Also, we have learned in C language. Okay, so in our C language class in freshman, first year student, I think most of you last year you have learned what is a C language. So in there is some pointers concept. And also there are some about uh, structures. Okay. So the same concept, pointers and structures, will be used in our chapter 4, linked list chapters. Okay. So there were very basic data structure array in chapter 2, and the other basic data structure is linked list in chapter 4. Okay, so that means that array and linked list are most basic data structure, and then we will apply this basic data structure into various application data structures. Okay, so stack and queue are also application of array and linked list. Okay, in this chapter, we will learn that stack and queue also can be implemented using linked list. Okay, in chapter 3, we have seen that how stack and queue are implemented using array, but in this chapter, we will implement stack and queue using linked list. Okay, and also I will give you one more homework. The same homework in the previous class, but you must implement your homework using linked list instead of array. Yes. So you must understand what is linked list completely in these chapters. Okay, let's go on. Okay, linked list are strongly connected with pointers in C language. So we can review the concept of pointers here. So if we have a list of 3-letter English word like ending in AT. So just like bat, cat, set, bat. So I have this 4 English word in my data. But I want to add new word, math, into this data set, into this data list. If these data are stored in array, then in order to store math, then we must move set and bet data to the right. Okay, so that means that bet, cat are stored in array. So originally there was a set and a bet, but if I want to add math into this list, then I must store math at these positions. So that means that set, bet must be moved to the right. So I can add math at this position, and the set is moved to the right, and bet is moved to the right. In this way, if we use array to store this data set, then it is not easy to add new data, arbitrary new data. Similarly, if we want to remove the word cat, that means that I want to remove this cat from the list. Then I must move this data to the left. Okay, so we must move set and bet one position to the left to maintain our sequential representations. Okay, so that means that if we use array for array data structure, then in general case, arbitrary insert and deletion can be very time consuming. Why? Why we need time consuming to insert and delete arbitrary data in array? That's because we must move the other data in our data structure array. Okay, so in order to add, we must move the other data to the right. In order to remove one data, then we must move the other data to the left in order to maintain our sequential representations. Okay, so that's the disadvantage of array data structures. Okay, so we can think new approaches, new data structures. So here is linked representations. Linked representations. So in a sequential representation means that it is array. In a sequential, the order of element is the same as in the order of the list. While in a linked representation, these two sequences need not be the same. Okay, so that means that in array, every data are stored in a contiguous memory space. Okay, so all of the data sequential data must have their ordered sequence. But in linked representation, these data are not stored in a sequential memory space. So this link, yes. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Yes, one more data here. Okay. This linked representation. This is a linked representations. This is a array. Okay, so quite different approaches of data structures. So in order to access some element in the linked representation, we must store address or location of the next element in that list. This address can be represented using pointers. Okay, so address and the pointer are almost the same meanings in C language. Okay, in array, the address can be represented using index 0, 1, 2, 3, 4, 5. This is called index. So index can be used to access some specific address. But in linked list, we must store where is the next element is stored. So we must know this address in order to access the next element. Okay, that is represented as link in the linked representations. Okay, so in list element, each list element usually contains both data component and the pointer component. Okay, so data component is our necessary data attribute, and the pointer will be used to make what is next element in the list. Okay, so these pointers are called link. Okay, so in C language, we are using this arrow to represent pointers or links. Okay, so in our textbook, in our class also, we will use this arrow to represent pointer or link. Okay. So this is a C language. Yes, we are very familiar with this operators in C language. So ampersand is called address operators. Okay, so that means that if we are given one variable, then we can find address of that variable using this ampersand. So ampersand A means that the position, the address of variable A. And the opposite of ampersand is asterisk. Okay, star symbols means that dereferencing or indirections operators. Okay, so that means that if we are using asterisk in front of a pointer, that means that the value of this address, Okay, so in that sense, it is called dereferencing or indirections. Okay, this is example. Integer I and pointer pi variable. Pi is assigned as i's address. Okay, so if there is I variable in the memory, and I will have value 10. And also this pi variable, pointer variable pi, will store the address. This is address of this variable I will be stored in the pi at this assignment. Okay, so %I returns the address of I, and it will be assigned into value of pi. Pi means that point variable of integer. To assign a value to I, this is a direct assignment, direct access. Okay, using variable itself. And asterisk pi is indirect access. Okay, so both method I and asterisk pi means the same contents. Okay, so this 10 will be assigned to variable I. 10 will be assigned at this memory space. And asterisk pi means that pi has the address, and the address's contents will be assigned as 10. Okay, that meaning are the same, all exactly the same. Okay, so 10 will be stored at this memory space. Okay, that was pointers. Okay, so pointer was studied in C language already, chapter, I think, 13. Okay, in C language. Okay, so you can review this pointer chapter 13 in C language again if you cannot understand this slide well. Okay, so let's go on. But pointer can be dangerous. Okay, so especially if one pointer variables are not assigned, we must assign null values to the pointers. So set all pointer to null when they are not actually pointing to an object, not initialized. Okay, so initialized when a pointer variable is not initialized, then we can assign always null values to the pointers. And also we must use explicit typecast when converting between pointer types. This is examples, integer I and integer pointer variable pi, and the pi will be assigned as address of I, and also pi can be assigned as memory space using malloc. Then size of integer, yes, so one integer size will be assigned, and pi will be assigned as this memory space. After that, pf is pointer of float. Okay, pf will be float asterisk pf will be declared here, and pf can be assigned as PI address, PI values. Or of course, these PI values will include address of I, but we must cast. This is called cast, type cast. Float pointers. This is declared as a float point variable. Okay, so cast an inter pointer to a float pointers. So that is explicit typecast. Okay, this is the first one, and this is the second one. And third one is define explicit return types for all functions. So pointers may have the same size of integer type, but function returning type default to integer, which can be later be interpreted as a pointers. Okay, so we must define one function return values explicitly. Okay, so that's the caution when use pointers. And in addition, furthermore, we must understand that most of the link will use dynamically allocated memory space. Okay, so that was in chapter 18 in C language. Okay, so you must review chapter 18 in C language again, and so when we do not know how much memory space we will use, or nor do we wish to allocate some very large area that may never be required. Okay, so that means that we do not know how much memory space we need, and also we do not want to waste memory space. Then we can use C provide mechanism called a heap memory and allocate storage at runtime, at execution time. Okay, in chapter 8 we have learned that we must use malloc functions to request the amount of memory space. Okay, and the opposite function of malloc is free functions. Free means that return the allocated memory to the operating systems. Okay, that is free functions, and that is about dynamically allocated memory space. Here is program 4.1. 4.1, and allocating and deallocating or returning of memory space examples here. So integer I and asterisk pi, float f and asterisk pf. So this is a pointer variable of type float. And pi can be assigned as dynamic memory space using malloc functions. And the size of the integer is 4 byte. And we must use typecast in front of the size. And pf also malloc. And the size of a float, yes, also 4 byte, but the type of this pointer is float asterisk. And then we can assign asterisk pi, indirect access of this memory space is 1024. It is an integer. And also asterisk pf, indirect access to the pf equals 3.14 float variable, real value, real number here. And then we can print pi, asterisk pi, and asterisk pf. Okay, that is indirect access or dereferencing. Okay, so after we use asterisk pi and asterisk pf, we can return the memory space to the operating systems using free functions and the free functions pf. Okay, you can run this program 4.1 by yourself. How you can allocate memory space dynamically, and after usage you can return the used unnecessary memory space to the operating systems. Okay, now we can enter to the new sections. It is called singly linked list. Singly linked. Single means that it is a one. So that means that there is only one link or pointers in this singly linked list part. Okay, so the previous data, bat, cat, set, and the bat can be stored using this link, singly linked list. Okay, so bat is the first element, and then this one data element consists of our data part and the link part. Okay, so this link will point to the next address, next element's address. And also the same way, this pointer will pointing to the next element's address. Okay, so the node do not resident in sequential location, and the location of the node may be changed on different runs. Okay, because it will be allocated dynamically. Okay, and if there is no more next one, or it is a last element, then the pointer will have null values. That means that there is no more next element in the list. Okay, so that is a singly linked list. Okay, if we use linked list, then arbitrary insertion and deletion will be very conveniently, very executed very quickly. Okay, so the same situations, we want to add a new word, mat, between cat and set. Then we must follow, we can follow these 4 steps. Okay, so we will allocate one node memory space. Get a node that is currently unused. Okay, and that address is a P address. Then set the data field of this nodes to mat. Okay, so this new node memory address is P address, and the data part of this new allocated memory is mat. Okay, I wanted to add this math to the list. That's our problem situation. And P address link field, yes, this one, will be point to the address found in the link field of node containing cat. Yes, this link memory space, this one, will be assigned to the link field of this math, P address. This is the first step. And then set the link field of the node containing cat to point to the P address. Yes, this one. This will be moved to this memory space instead of this one. Okay, so this step is 2. Okay, and this sequence of this first adjustment and the second adjustment, we must follow strictly the sequence of this first and the second. If we reverse the order of this sequence, then it makes wrong. Okay, so if we change the address of cat's link field to this one, then we do not know where is next of this one, because we already lost this link field, and at that time all of the following data becomes orphanage, orphan, or it is called dangled. So that means that it lost its parent, lost parent. So orphan means that lost parent. Okay, so we must keep the sequence of this this first one and second one. So that means that in these steps, third step must be precede fourth step. You must keep this sequence. You must first execute the third step, and then you must execute the fourth step. Okay, that is insertion of new data to the singly linked list. Okay, and how about delete? Okay, so we wanted to delete newly inserted math data. Then find the element that immediately precede math. Okay, immediately precede means that what is a one step earlier element of math. That is a cat. Okay, and then the link field of this cat, this one, will point to the math point, this one. Okay, so this one. Yes. If we change the link field of a cat to this one, then this link will be lost. So that means that this math becomes orphanage, or it becomes garbage. Garbage. Why? Nobody can access to this memory space, because there is only one way to access this one, but this one is already lost. Nobody can access to the math data. So that means that it is called garbage or orphanage, open memory space. Okay, but we can see that arbitrary insertion and the arbitrary deletion can be executed very, very fast in compared with array. In array, we must move all of the data to the right when we add a new data, and all of the data must be to the left when we remove one existing data. But in linked list, there is no necessary to move data in these data structures. Okay, in that sense, linked list is very convenient when we insert or delete arbitrarily. Okay, that's singly linked list method. And how we can implement this singly linked list. Okay, so that is here type def structure. Yes, we must define one structure list node, which include data part and the link part. So every data we want to store will be represented using data in here. And also we already know what is a student data, student attribute in the previous homework. So all of the student attribute can be stored at the data part. And the other part is point part or link part to point next element. Okay, that is list node structures. This is a structures. Okay, so structure is studied in chapter 15 in C language. And one point, list point, will be defined as point of list node. Okay, so the first list pointer is first and second. And there are three functions: insert and print list, delete list. Okay, so we can see how we can implement these operations, these functions. Okay, this is the implementation of previous singly linked list. Okay, so this one is using malloc and add first list 20. The data is 20. Then first is allocated as size of first memory space, and first data becomes 20, and this is the last element, so the link field must be null. And then print all of the data, print first. That's the first step. And the second one, I want to add one more data, 70. Okay, so that means that this new memory space is assigned, and this memory space will be assigned as a first. And the first data will be 20. And that is the end of this one. After that, I want to add one more data, so 70. And 70 will be assigned to the second one. And the first link, this one, originally it was null, but this link field will be assigned as the address of a second element. Okay, so at this time it is null now. And print first. Print means that I want to print all of the data in the list. So we will start from the first data, 20 and 70 will be printed using these functions. And insert first okay, next one is that insert first and the second. Second is 70, so that means that insert list 70 rather than 50. Why there is a 50 here? So after second node is 70 here already, and I want to add one more data here, 70, okay, because it is a second one. And then this link field will point to the 70. And how about this one? Insert first. First value, data value is 20. Okay. So the link field of a previous node will point to the first one. And delete after second node. So that means that I want to delete, this is the first address, and the first element of address second, and the second link. Okay, so second link means that this is a 50. This is the second one will be deleted. Okay, how you can delete? Okay, so here in deletion, in deletion, if we delete this second element here, then we will just change the link field of this previous element to the next field. Then this link becomes lost, and this memory space becomes non-accessible, or it is called lost, it is called garbage, it is called orphan. Okay. And delete the first and the first link, so that means that 20 will be deleted. So that means that first will point to this one directly. Okay, so we have only 70 and 20 here after this one. And delete the first, yes, delete first after this one. And delete the first and the second. Okay, so we can delete this one, second one. So now we have only 70. This is a first. And this is a no. We have only one node after these deletions. Okay, so you can type all of this source code to your compiler, and then you can execute yourself. It will help you to understand the dynamic memory allocation, and also it will help you to do your second homework. And the other insert, okay, this is insert functions, and insertion function uses malloc to allocate the memory space. And oh, the data itself is fixed here, 50. Okay. And temp access link. Access link becomes temp. Tempus link equals access link. Yes. So this insert means that I have one link first, and there is some element, the address is X. So this insert function try to insert new data, but new data is fixed here, 50. Okay. 50 will be allocated and stored here, and then tempus link will be assigned as this link will be copied to this one. If it will point here, then this one. And access link becomes access link. Yes, this one. Access link becomes temp. So this one instead of this one. Yes, this new data node was inserted using here. And else, that means that there is no element. So this is the first node, first element in the list. Then temp null becomes null, and the first becomes temp. Okay, so this is insert function implementation, and delete function implementation. Also, it has first element and the trail and the point list X. So that means that I want to there are one linked list. First one is a first, and this node is a trail node, and this node is X. So originally this one is pointing here, and this also has next element here. Then I want to delete this X. Point options, ink color. Yes, I want to add this X. Then I can adjust the link of trail, this one, link of trail as access link, this one. Okay, this one will be assigned instead of this one. Then this X becomes garbage directly, immediately, because there is no access method to this memory space. Okay, that is delete functions. Okay, and print list. Print list means that the parameter is only first pointers. So that means that I want to print all of the data from this linked list. Okay, so they uses this loop, infinite loop. There is nothing initialized first, and the first will be print until first becomes null. Okay, and then first becomes first link. So that means that there is a link here, and this one, and this one. Okay, so first one is here. I want to print all of the data here, then it will print the data at the first element here, and then goes to the next element, print this data, and then goes to the next element, print this data until this value is null. Okay, so this part is very, very important when I want to traverse all of the data. All data in the linked list, then we must use this for loop. For loop condition in here is very, very important, and you must memorize this for loop. Okay, so I must visit all of the data in the linked list, then we must use these structures for loop. Okay, so in that sense, this one is important one. Okay, that's the implementation of a singly linked list.